So tell us a little bit about your team and then the project that you've been working on for the past year.
All right, so our project was image processing by FPGA. So the idea was that eventually you would have a self-flying quadcopter that would be navigating itself by use of a camera and image processing on board an FPGA. And then the flight controls would then be controlled by the FPGA. So basically our team dove into the image processing side of that. So basically we would take in the image, do any processing on the image, such that we could detect where an object was, and then basically output where the object was and its location. So then another team could come in and do more controls work to show that this is where the object was, and then being able to have a quadcopter that follows it around and keeps the object within the frame.
Okay. And so could you go into a little bit more depth of what you guys have done, like in the coding and the hardware side of this?
Yeah, so basically the first idea we had was to do full brisk object recognition and detection, and then do a whole full custom hardware layout for that. And then that ended up hitting some snags. So we ended up going with a kind of a in-between method where this Pink board has, it's got an ARM core and an FPGA on it. And there's a built-in framework called Pink that is an open source project that allows you to do image processing and certain things on the ARM core, but using the FPGA for optimization. So basically our idea was that we would use their drivers to have the HDMI in and out, and then we would write a custom piece of hardware that sits in between those that detects a red object and then outputs its location to the screen. So we would have a custom piece of RTL written in Verilog that performs that operation, and then we would use that inside the block diagram of the Pink architecture so that we can use their drivers and their overlays, but then have our piece of custom hardware in the middle of it.
Okay. So after working on this for a whole year, what would you say was probably the most difficult part of this project?
I would say just the compatibility issues and the getting our hardware to work with the Pink architecture, because it was already a fairly complex architecture that they had set up on the FPGA and the ARM core. So being able to get our part to kind of work with those and interface with their pre-made interfaces was probably the most challenging part. So we ended up kind of changing our approach to it a couple times because of that, and kind of ended up on this where we're at here, where the image processing is actually for the most part happening in Python on the ARM core, and then we're using the FPGA for the drivers and that type of thing.
So what did you think that you learned most from this project, like that you didn't know before, or you think that would be really helpful for you going forward in your career?
I think one of the big things is just kind of learning how to deal with challenges and different things that come up. We had some hardware compatibility issues and some different deliverables that we were trying to get based on some other teams that didn't quite get done. So I think one of the biggest things for me was just learning how to be adaptable and be able to kind of pivot when problems occurred. And then I think the other big thing was just kind of realizing when it comes to hardware design, a lot of the things that seem like they should be a really simple problem are actually kind of quite complex and have sneaky things that can catch you. So
it's always a hardware problem, right? Yeah. If you had probably more time to work on it, like say you had another semester or another year, is there anything that you would want to add to what you already have, or anything that you think can be improved to it?
Yeah, certainly. I think from the start, I think this was kind of designed to be a multi-year project where another team could kind of come in and pick up where we left off. So I think there's certainly a lot of interesting work to be done. I think one of the biggest things would be the quadcopter controls, that another team could come in and use our image processing and then actually strap this board to a quadcopter and use it to control the motors based on our image processing code. So I think that would be kind of the biggest thing that I could see if we had more time. I think it would be interesting for us to go ahead and implement.
How long do you think that would take to implement? Is this something that could be done for the next senior design year, or is it like even more out in the future, like 5 years, something like that?
I think it kind of really depends how deep you want to get into it. I think if somebody came in and wanted to do a controls project on it and just kind of have a basic flight control that followed an object, depending on what their backgrounds are and how much things have progressed. Even since we've been working on it, there's been a big update to this architecture in the midst of our project. So I think even if that comes even further, that'll give them more tools to work with and better tools to work with. That I think you could get something going in the next year, but I think certainly there's always room to go. So I think if they pushed it further and then another team could come in and pick up where they left off, I think there's a lot of room in this area to have a lot of interesting work.
Cool. Awesome. Well, thank you for coming in and explaining your project to us, and good luck to you guys for the rest of demo day.
Awesome. Thank you.
So could you give us an introduction to who you guys are and what your project was for the past semester, or past year, I guess?
Sure thing, yeah. My name's Jordan Rogers. We are Team 15. We're working with Microchip. Teammates are Colby, Jake, and Chris. We developed an autonomous field line painter unit. So the purpose of this device is to essentially paint field lines, such as lines for a football field or a soccer field, autonomously, and then have some self-correcting mechanisms.
Okay. So could you go into kind of more detail on what you guys have done through the past year and like the process of how you got to this final product?
Yeah, sure thing. So the first 6 months were all spent pretty much doing basic research, looking at current models, looking at how current field line painters are developed and how they're made to work. And so that was the first 6 months, kind of designing and kind of analyzing how the things work. And then starting in about December, January, we started putting stuff together. We divided it up into 6 subsystems, namely the drive system, the physical structure, the sensor system to detect its position, the airbrush system to paint, and the central control system. So those were the main systems we developed, and then from there we kind of divided everything and yeah, put it together. Over the last month or so has just been refining and iterating, redesigning some things that didn't work exactly to plan.
Yeah. So could you kind of explain how this thing would work then?
Yeah, sure thing.
Yeah. Yeah.
Okay, you can, yeah. Perfect. So back here in the butt, there's a button to turn it on and get it started, which I can actually go ahead and do. Once I press this button, this little cylinder here at the top will start spinning, hopefully. Yep. So, well, the rubber band's not supposed to break off, but
Yeah.
essentially what it's doing there is it is inside this little cylinder there is a laser and then a photoelectric diode. So it shoots out a laser and looks for 4 posts that we have set up in the field.
Okay.
Yep, and so when the laser hits that post, it bounces back, and then using that, it can calculate its angle. Using that, it figures out its position, and then that helps it figure out where it is relative to where it's supposed to be, you know.
Is there a max distance that it can sense where the post is?
Yes, there is. The max distance is about 30 feet or so.
Okay.
One of the issues we ran into with this device, of course, was we designed a full-scale model, like a normal size to paint, you know, a 100-yard football field, and we found that it was about $1,500.
Yeah.
So a little more expensive what we could do. We decided to go ahead and just scale it down. So this is what you see here. Right. This we designed to paint probably about a 10-yard field. So we scaled it down by about a 1/10 as far as painting design. Right. But yeah, the posts go about 30 feet or so, so it has good range. One of the issues we ran into is that the detection system isn't perfect. It has about a 3-degree angle variance. Okay. So we run into some issues there, but yeah.
Okay. And so how does you said there's like self-corrections, obviously, you know, if it hits a bump or something, it might not maintain the straight line. How does that system work?
Perfect, yeah. So the main design is that we give it, so for example, let's say we give it a square to drive. So it'll start driving the square. As it's driving the square, this sensor system is going to calculate the relative angle to the 4 posts. Okay. And using that, it's going to calculate its current position relative to where it should be, because we have where it should be, because we give it a square and then.
Right.
and then yeah, figures out where it's supposed to be, and then if it sees that it's not where it's supposed to be, it stops the motor, calculates where it's supposed to be and the corrections it needs to take, sends that to the motor, and the motor either backs up or just self-corrects a little bit and then keeps it on the path.
Okay, awesome. So throughout the course of working on this project, what do you think is the thing that you learned the most from this whole experience?
I think the one thing I learned the most probably was the importance of having a plan, of having an idea in mind, of having good goals laid out, having a good solution laid out, and then working on that. We ran into a couple issues of problems where we tried to do too much, essentially.
Yeah.
And so I would say, yeah, how to plan. I think that was probably the most important thing I learned.
That's definitely something you could take into industry. What would you say that the hardest part of this project was? Like, it doesn't have to be, technical. It could be something, communications wise or, soft skills wise, but overall, what do you think it would be?
Yeah, I would say, yeah, communications was actually probably one of the biggest problems. That and getting the drive system working, because none of us are mechanical engineers. We're all electrical engineers. So we all had to learn a little bit about how motors and stuff work. But yeah, communication was probably one of the biggest areas where it was just more difficult than expected. It was hard to communicate stuff. And I think that could have been solved just by planning better and having a better schedule and following the schedule.
All right. Awesome. Well, thank you for your time, and thank you for showing us what you guys have accomplished this semester and last semester. And good luck to you out there demoing it to everyone else.
Appreciate it.
Thanks. Hey, how's it going?
Good.
All right. So could you introduce yourself to everyone and go into the project that you've been working on for the past year?
Yeah, of course. So my name is Jacob Peplinski. In our project this year, we worked on building a real-time LPC vocoder. And so all a vocoder is it's a musical tool that you can use to blend a speech and an instrument signal together. And so it's kind of borrowed from the telecom space, but you do a certain amount of math to a speech signal and then to an instrument signal, and then you do that in real time, and what you get at the output is actually sort of a blend of the two. So we're using it, just as a musical effect in this project.
It's kind of like auto-tune.
Essentially, yeah. It ends up sounding a lot like auto-tune.
I got it. So, so what have you guys accomplished this semester? Like, what is your end product now? Obviously you don't have the full thing here.
Yeah.
But what are you guys demoing out there to everyone else?
So we actually have the full vocoder working in real time. So people who are here to view the project will be able to pass by. We have a keyboard set up and a microphone set up. And they'll be able to play the keyboard and speak into the microphone at the same time and actually hear the output of the vocoder. And so, yeah, so it works just about as well as we wanted to. So it's sort of a job well done, I guess, in our books.
Yeah, that's awesome. What do you think was the hardest part of your project?
Yeah, so the this project is, if you could put it into a category, it's kind of embedded programming. So we had an ARM 32-bit processor that we had, and the majority of the information required to program those things is kind of buried in industry. So there's code to actually use those things well. Like, companies don't share because they make products that actually use that chip.
So you can't find it on the internet as like reference.
Yeah, so we kind of had to resort to reading the 1,000-page manual to the chip and kind of figuring things out on our own. So it was arduous, but we got it finally.
Okay. Yeah, that sounds like quite a task.
Yeah.
Looking back, what do you think you learned the most out of this experience?
I definitely learned how to. This is my first experience, and it seems like electrical engineers don't get a lot of experience, programming hardware directly, and so it was kind of nice to, take a whole year to really learn one piece of hardware, and so I'm really comfortable working with ARM processors now. So that's kind of cool. That's kind of useful in industry. So kind of glad that I got that out of the project.
That's good. So now that you've gone through this whole process and you have this year's worth of experience, if you could start back at the beginning again, is there anything that you would do differently now that you know with hindsight how everything works?
Yeah, I probably would have started programming a little bit sooner, even if I didn't know the code would work. I spent too much time reading, and then I didn't really start the programming till the second half of the semester, and I think it'd be more useful to get my hands and feet wet, kind of first thing first. So yeah.
Okay, awesome. And then, so if you said you have a full working model, it works everything, but if you'd had more time, like say an extra semester or even an extra year, is there anything that you would want to add to this, or is there any way you think your product right now can be improved with the extra time?
Yeah, so I guess if I'm being nitpicky, the case that we're using is kind of big. I'd like to, sort of the point of the project is to be portable, so I'm hoping that I can get it into a case that's at least kind of, palm-sized. I also want to, there's one parameter that you can tune in there that'll kind of change the quality of the vocoder, and so I want to be able to, like have a pod on the outside where you can actually change, yeah, so you can kind of see, how this one parameter affects the output quality, so that'd be kind of nice to have too.
So how does your product compare to like products that are already out there on the market? Like, is it cheaper? Is it better? Is it like, well, what makes your product stand out?
A couple things. So cheaper and just sort of unique itself. So linear prediction, or LPC, it's something that's used in telecom a lot to actually like transmit speech like over the wires. So there's other vocoders out there right now to do music stuff, but they don't use LPC specifically to do vocoding. They use other stuff. So this is really one of the first things that I've seen that actually uses the vocoding from telecommunications itself to make a musical effect. And also it's pretty, I mean, it only costs like $20 to make. That's, the board's pretty cheap. So
okay, awesome. Well, thank you for coming in and sharing your project with us, and good luck to you demoing out there to everyone else.
Awesome. Thanks, Richard.
Cool. Sweet. Thank you. Whoa. All right. We'll have a lot to talk about with this one.
Sure.
All right. So we can start by introducing yourself and then kind of what your project was for the past year.
Right on. So my name's Cannon Smith. I'm part of the electro-optical team. What we've got here is we have built a UAV. So we followed the idea of a general unmanned aircraft that flies and is able to monitor things on the ground. So what we constructed this entire thing ourselves. It's all focused around this Pixhawk right here, which essentially we take this plane, we throw it up in the air. Well, we launch it essentially, and we have the option to control it by ourselves if we'd like, and then we also have the option of having it controlled completely by autopilot. And the idea of this is this Raspberry Pi right here has a camera that's undermounted right here, and so while it's flying, the user on the ground with a laptop, it's controlled via radios. We can take pictures, and then post-flight, those pictures can be run through a code that we have been using over the past year, that it will take objects in those images and it'll classify what is exactly in those photos. Oh, okay. So our goal we were thinking of was, imagine if you had a farm and you wanted to count your livestock that's in the field, but driving takes quite a while, right? So you would launch your plane, it would be flying on its own autopilot, and then it would be able to capture the images and count your own livestock in your own field. And then it's got your return to base. It's got your airspeed sensor right here. This allows it to avoid stalling. It auto-corrects itself. It's got sort of like a flight assist. So if the user is not really experienced, it'll auto-balance itself. And that way it helps the user a lot. That way we can focus on just the imagery side of the project.
Okay. So is the imagery, is it kind of like machine learning where it's like,
Definitely.
yeah, so like you're trying to classify different animals based on, what you see from the pictures?
Yep. So what we've done is we had a code that was originally based, it was trained on 1,000 images, or 1,000 objects. And so what we've done is we took the time to learn sort of how it works, and we've retrained a layer in this model to add our own objects. So what we've got in the demo room right now is some soda cans, and we're able to run those soda cans through the model that we've trained, and it will differentiate between soda brands.
Oh, so like Coke, Sprite, stuff like that.
Exactly. Okay. So that's the idea, and we have also a live stream code that outlines the objects that we're classifying, and it tells you what's there. So if we had more time, that's what we would be doing with this. We would integrate that onto here so that it would show a live feed back to the user on the ground and classify objects as it's flying.
Awesome. So this seems like a pretty intensive project. So what do you think was the most difficult part of this project overall?
One of the most difficult things was just interfacing all of these electronics to get the plane to work. We crashed 3 of them already. So we had to rebuild multiple times because we had to deal with, this is our first time using an airplane, so we had to, the center of gravity, we had to balance all of that. We had trouble with the autopilot, especially in the beginning. So we crashed a few planes, and the software, how the radios talk, that we had some issues with connectivity there. So the plane itself was a lot more difficult than we anticipated.
Yeah, seems like a lot of stuff working in conjunction, which is always hard to get working together correctly.
Definitely. Trial and error.
Yeah. What do you think you learned the most from this project? Was it getting all the equipment to communicate correctly? Was it, coding the machine learning algorithm? What do you think was something that you learned the most out of this?
While the coding, everything, we did learn a lot. We still don't fully understand how it works because machine learning is so intense. Right. But one thing I think that's the most valuable for us as a group was we took a real world problem, sort of with the whole farmer and counting its livestock, and we created an idea that would solve that problem. So I think we kind of learned how it works in the actual engineering field. We have a problem, we look for a way to solve it. So I think that was the cool thing that we learned.
That is pretty cool. And then finally, if you did have more time to work on this, is there anything you would add to the current model that you have right now that you think would improve it?
Definitely. We would look to find either a better camera or probably just that, because a lot of the objects that we classify, it depends a lot on resolution and distance of objects. So we can get the plane to fly low, but if we don't have a good image of the object we're classifying, it struggles. So we want to do that, and the live feed stream, like I mentioned earlier, that would be awesome.
Okay. Awesome. Well, thank you for bringing this in and showing it to us and explaining how it works, and good luck to you out there for the rest of your demo day presentation.
All right, thanks.
Hi. Can you hear me?
Yeah, I can hear you. Can you hear me?
Is there volume on here?
Yeah, it's up all the way. Yeah, it's up all the way. Speakers, that help? Can you hear us now?
I can hear you.
Okay, cool. We can hear him too. Awesome. Okay, speakers are there. All right, so could you introduce yourself and then talk about the project that you've been working on for the past year?
Yeah, sure thing. My name is Christian McCollum. I am with the VLF team, number 19 at ASU. The past 2 semesters, ASU have been working on creating a small electrical device that can detect VLF signals from DC to 100 kilohertz. Our goal was to design a receiver with an antenna attached. We created 3 different antennas for 3 similar Arduino setups or circuit setups. And then we had plans to attach that payload to a UAV, who we paired with the EO team, team number 20 at ASU, to fly the UAV and then collect data while in the air to detect those frequencies from DC to 100 kilohertz, and then to analyze that data after the plane landed.
Okay, so what is the motivation behind, how is this used in, I guess, everyday applications, or like what?
So like certain applications that this could be used for, or that has been used for in the past, is with telegraph lines and power lines and radio signals. All those applications are use VLF signals to or generate VLF signals that can communicate between devices in the past. This particular project, what makes it unique is that we were trying to gain some military attention, or use it towards military applications by using the implementation of UAV or small UAV drones, which hasn't been done. Not too much research has been done into it today, just because the recent development, all the smaller drones that are being used, available from like police forces and military such as that. So our goal is to attach it to said UAV device with our VLF detection to possibly detect underground bunkers or underground power sources in territories that are unfamiliar to troops, so to speak. And then they can gather that said data after the drone landed, or if you wanted to create a receiver end that can generate the data while in mid-flight, it can be used in that sense too. In this sense, we created one that can just store the data while in flight, and then we could decipher that data once it landed using a data storage device using a SD card.
Okay, awesome. So after going through this whole process, you know, for a whole year, what do you think you learned the most from doing this project?
I think what I learned the most, and what I think my whole team learned the most, was kind of like working together as a team, managing time management, and kind of learning how from step A to Z to create like a plan of action, and then to follow that action through with a device that, you know, none of us have ever, you know, created such a thing before, and it was really unique to base our research off of the Stanford Johnson paper that we referenced from in our research, and then to build that, like the receiver and all that in the lab and at home, and then to be able to actually, you know, pick up signals that we planned to set forth and detect. It was really cool. We did have flight complications with the UAV, so I mean, we were unable to use the flight or the UAV model, so to speak, but everything else was successful in our design. We also updated the UAV model for future teams with a more stable flight model than the X-Wing that we used. It was just really difficult to fly, I guess.
Okay. And you guys are a hybrid team, correct? So you have people on campus and people online. So could you...
We have one official on-campus member, and then another member that lives like 20 minutes away. So there are on-campus members deemed for the project, and then myself and James, who's also on the Google Hangout, we are online.
Okay, so could you kind of talk about some of the, maybe, were there any issues with being, you know, half of you on campus, half of you online? And was there any communication issues, or did you learn anything from the experience of just not working with someone that is, you know, physically there?
Oh yeah, I mean, it's some of the issues incurred with like kind of designating who to do what, because in my particular case, in James' particular case, you know, we don't have some of the same equipment that's located on lab with the GWC lab campus for electrical engineering. So there's certain things that we couldn't do, but we managed it in our own sense by gathering components that we know that we could have created on our own. And, you know, and I got like a soldering kit and kind of took some time to learn how to solder, even though I had never soldered before. So there's certain things that, you know, you had to like get by, but, you know, working with the team and then shooting ideas back and forth, I think it made it a lot easier because there's 4 of us as well as our team mentor. And it's better than just, you know, tackling one person, doing this whole thing, because I think it would be way too difficult to tackle it on your own.
Right. Okay. And then finally, final question would be if you had more time to work on this project, like say another semester, is there anything that you would add to it to make it, that you think could make it better, or that you would want to add to it just, you know, because you have the extra time?
Oh yeah, certainly. I mean, if we had the extra time, again, we would probably want to do some more test runs with the UAV, get a working UAV model that wasn't so unstable in flight. So definitely that for the most part, and then, you know, attaching the payload, which is our electrical device. Furthermore, we could have, you know, analyzed it further by trying to create the device even smaller than what we created it to be, to maybe even more flight stable, so to speak. But again, we kind of ran out of time, and the plane model that we chose wasn't as successful as we wanted it to be. But in the future, we could have done that for sure.
All right. Well, awesome. So thank you for your time and, you know, sharing your project with us, and good luck to you guys out there for the rest of your demo day presentation.
Oh, yeah, thank you.
So could you introduce yourself and then tell us about what you guys have been doing for the past year?
Yeah, so I'm Nathan Gardner. Yeah, so this is our project. This is the robot. This is just part of the project. So the idea is we wanted to model what it would look, what electrical vehicle charging would look like in the future. So when everyone has an electrical vehicle, what's the load going to be like on the power grid when everyone charges their car at night? Along with smaller details of how are people going to be able to charge their car autonomously when GPS doesn't have that much accuracy. So what this robot does is it's a two-wheeled balancing robot. It auto-balances itself, but it has this color recognition sensor on it, object recognition. So it will recognize these colors, these color shades that I set it to, and then it has a sonar sensor on it that allows it to get within a certain distance of the target. And then you can see here that it has a little inductive.
Can you lift it up a little bit?
Yeah. You can see it has a little inductive, was this a receiver? And we have a charging station with the transmitter. And so what this is able to do is it's able to find the charging station, well, autonomously roam, find the charging station, and self-charge itself. And the idea is it can be scaled to multiple more robots, however many you need to be able to model what would happen if all the robots charge at the same time.
Okay. So what does the whole color recognition thing do exactly?
So what it does, is you can set a color code within the programming of the camera itself. And so it outputs an analog output to the microcontroller, basically signaling where it is on the x-axis. So if the image is on the far right of the screen, it sends a signal of 0. If it's on the far left, it sends a signal of 800.
Okay.
Allowing the robot to be controlled basically by the color code.
Okay, so is that how it recognizes where the charging station is?
Exactly, yeah. So the idea is if a Tesla wanted to be able to charge itself, it could have a color code above the inductive charging pad. And so it would be able to navigate towards the pad within a centimeter of accuracy.
Okay, cool. So could you kind of go through, like, what kind of components are in your self-balancing car right here?
Yeah. So some of the main components are obviously the motors. They have encoders. And so that allows the feedback into the microcontroller to allow it to self-balance. I can actually show you the self-balancing feature. So the code I have loaded into it right now is it should navigate itself to the color code. So what's going to happen is it's got the motors. Okay, so it should self-balance itself, and then we'll try to. So basically what's happening is it is getting feedback from the encoders as to the angle that it has a gyroscope as well, so it's getting a feedback as to what angle it's at and how fast it needs to move the motors in what direction. And so it has that feedback system.
It's pretty cool. So there seems to be a lot of components that go into this. What do you think was probably the most difficult part of this project?
I mean, obviously coding it was very difficult, not being a programmer. I'd say the most difficult part was I actually broke the voltage regulator on the microcontroller.
Okay.
I reverse biased it with the battery. So it was hard because I had to debug the MOSFET itself, and then I had to replace the MOSFET and then bias it myself. Okay. But I mean, it was difficult, but it ended up working out, and I didn't have to buy another part. So, but yeah, definitely the coding was the most difficult.
Do you think you learned the most from the coding, though? Like, even though it was so difficult, like, is that the one thing you've probably learned the most about during this project?
Oh yeah, for sure, without a doubt. Without a doubt, I've learned so much more about coding and how feedback systems work, how to be able to integrate your own systems on top of an existing system. This is actually the base robot I actually bought off Amazon, but I was able to take whatever base code they had and add in everything that I needed to be able to get the image recognition and the autonomousness to work.
Okay, cool. All right, well, thank you for coming in and telling us about your project and showing us how it works. The demo was pretty cool. And good luck to you for the rest of demo day out there.
Awesome. Thank you.
All right. So could you tell us who you guys are and what your project was?
Sure. I'm Michael, and we are the Smart Vehicle Detection Project. So our project was trying to sort of target a problem that has really become big in the news lately. Ever since that Uber accident where the car hit a pedestrian, we're seeing that the safety of these algorithms that are being deployed on these commercial systems affect everyone. Every member of the public is a stakeholder in these, computer vision, sensor fusion, and decision systems algorithms being as safe and effective as they can be. So we wanted to target a way to help democratize the process of building these by driving down the price, because right now the units that are used to collect that data are prohibitively expensive. Like, for example, the rotating LiDAR on top of the Uber cars is $80,000 unit, I believe. And the units that like Waymo use are also like 32,000. Regardless, prohibitively expensive for like a university research group. So we've made a system that is $1,000 using a LiDAR unit that has yet to be deployed commercially because it's very cutting edge, created by this startup called LiDAR Tech. And we built a system around that with a camera and stuff and demonstrated some basic sensor fusion on this sub $1,000 unit that can be used by university research groups and stuff to collect data sets that can then be used to build a big corpus of data sets of these matched LiDAR data and video that can then be used to develop new algorithms and drive that process being democratized.
Awesome. So do you have a video to show?
So this is a video of just the so here what we're just demonstrating is sort of the quality of the data by overlaying distance measurements on top of the video whenever we get LiDAR distance measurements that are out like at a certain distance. So for example, you see here we have we're picking up 40 meters-ish out by those cars across the street, and as cars are coming across, they are sometimes picked up. Now you might ask, this seems kind of low quality, right? If this is all we're detecting, how useful is this? Well, that's sort of where the decision algorithms would come in. So for one thing, a lot of this data has not been processed at all, other than to render it in a format that makes sense to a viewer overlaid on top of this video. But, with a lot of techniques, filtering stuff to denoise the signal, you can get a lot better measurements. And also we found some issues with our mounting scheme, because right here, this is the way that we are currently mounting it. We have these suction cups. Do you want me? Sure, I'll take it.
Yeah, so I don't have to reach.
Yeah, that's fine. So we have these suction cups here that mount up on the inside of the windshield of the car, and that causes a couple of problems that we didn't foresee. The reason why we selected this procedure was because we didn't want to put this $1,000 apparatus on the outside of the car and have it be exposed to the elements and stuff, and also have like USB cables reaching in through windows and stuff. But the reason why we're going to have to do this is because the way that a LiDAR works is it emits a infrared laser pulse and does a time of flight measurement for the return of that pulse. The problem is in the angles on the video that are, closer to the center of the video, the problem is those laser pulses are hitting the windshield at a normal angle. And, whenever you shine like a laser on any ray entering a surface, a semi-transparent or transparent surface, an element of it is going to be reflected back, and then an element is permitted. The problem when it hits normal is that the reflected back element will cause it to get a much shorter time of flight than the object that is further out, because it'll just detect the windshield. Obviously that's a problem. So we're going to have to mount it on the outside in order to overcome that. However, at the outside distances, it's a little bit better. But we have submitted a poster presentation proposal for AUVSI I think it's Autonomous Vehicle Symposium, which is in July, and we'll be hearing back soon about whether we're admitted for a paper. So
that's pretty awesome. So after all this, what was the one thing you learned the most from this experience?
So I learned a lot about the software development process because that's something I was the most software inclined of the people on the team. So a lot of the development tasks sort of fell on me, but I was not ready for some of the difficulties that we ran into, especially with dealing with these different SDKs that are produced by these different manufacturers, and all the poor documentation and stuff. It's really been a lot of learning there on good practices for software development. So I guess that's what I took away from this.
Awesome. Well, thank you for sharing your project with us and telling us how it works, and good luck to you for the rest of Demo Day.
Thank you.
Awesome. So could you introduce yourself and tell us a little bit about what your group has been doing for the past year?
Okay. So my name is Hubert Baserdo, and we're actually sponsored by General Dynamics, and we're working on a phase lock loop simulation tool. So, we're good? Yeah, okay. So our team members is myself, Eric Roden, Tim, and our mentors are Paul Hale and Anthony Medica. Those are our sponsors, or our mentors throughout this project. So the whole purpose of PLL is to make sure that we're locking two signals and just try and make sure that we reduce any phase noise. And that's the whole purpose of a simulation tool, is to be ready for any space applications. So for PLL purposes. So the whole reason the company wanted us to develop this was to to make a custom program for the company to make any PLL softwares for payloads. All right. Okay. So our project, right? So our project was developed in an Anaconda 3 Python, and that's where we developed the GUI software. So that's just a friendly user interface that we developed for the company. So next slide. Sorry. Okay. So this is actually going to be our main GUI here, and that's what we developed. We were kind of modifying an Excel spreadsheet that they're currently using, and we want to make something that's a lot easier for any engineer to come in and use. So this is kind of a background here of what we did to make everything simplified. So there's actually a lot of components in this GUI, like a noise pages, and we got certain plots for each one. So the whole purpose of it was to kind of match an actual PLL device that's being used in some projects right now. So that was the whole reason, to match our software to that, to make sure that it's very, very precise. So this is going to be our filter page. So here we actually have a passive, we have active A and active C filters. These are the and a Butterworth filter. So these are currently the 3 filters that we're able to produce. All right. So to actually test the device and verify results, we actually brought a FSWP, which is a phase noise analyzer, and that's actually the PCB board that we brought that's over there at our table. So this device here is capable of getting very precise information about the phase noise, which is used throughout the company. So, okay. Yep. So this is the results that we got from the FSWP. I'm sorry. No, yeah. So this is the results we got from the FSWP. We got a spectrum. We got a result from the spectrum analyzer, which actually shows the locking at 8 gigahertz. Mm-hmm. So we have that, and then to the right is actually going to be the composite phase noise, and that's what we're trying to match for each for each frequency, which is matched to the tool. So the whole point of this is just you want the wanted signal to be at that specific lock frequency. So that's going to be 8 gigs, which is the wanted signal, which is actually the carrier. So purpose of the tool too was also to get the noise jitter as well. So
Okay.
So this is actually comparing our tool to a data sheet and the results from the FSWP. So here to the left is actually our results that we got from our program. In the middle, it's going to be the results from the FSWP. To the right, it's going to be the data sheet from the HMC 704 from Analog Devices. Okay. So, yep. So the whole purpose of this tool was just to create a user-friendly tool, which right now we're going to be doing more testing, and hopefully that this will become a foundation for General Dynamics. So.
All right. Awesome. So throughout this whole process, what was the most difficult part of this project that after going through everything?
Right. So the most difficult part was actually going through the formulas. We didn't know how extensive that actually is and how many different and how hard it actually is to program all that together too. Because we received data sheets, well, and like some software that they use, but even that was very complicated for us to learn right away. Because it's not just a basic PLO, it's actually for space applications, so it needs to be very accurate.
Okay. And what do you think you learned the most from this? Was it like all the programming skills from this?
Yep. So throughout the whole time, we actually, each member learned how to program a lot better. Nobody knew how to properly, design a GUI or anything from scratch, so it was a big process.
All right. Cool. Well, thanks for coming in and sharing your project with us, and good luck to you for the rest of Demo Day.
Thank you.
Introduce yourself and then talk about the project that you've been working on for the past year.
Sure thing. My name is Mohammed Finzer. Our senior design project is called Power Crates. The fact that it's called Power Crates, you'll get to know very soon. It's basically an off-grid power system. So here are my team members. We have Salar Chauhan, is like presenting our president right now, Daniel Butler and Ahmed Amr, and our mentor is Dr. Stuart Bardin. So the reason we decided to do this project is we were talking to Stuart Bardin on our initial days, and he was like around 40% of the Navajo Nation community, they don't have access to electricity. Okay. So we were very fascinated by the fact that like in this 21st century when electricity is such a huge thing, people don't have access to it. So what we set out to do is create a very reliable system where they can use the solar energy using the power PV modules to power their homes. All right, so these are our goals. Our goal is first to design a PV system that meets the specified load requirements. And the second important thing too is to implement a monitoring system. So we just don't want a system there, we want to monitor how it's working. Right. So we'll be using a Raspberry Pi to monitor those systems. So it's called, this is a basic layout of a system. So our two PV arrays are connected in series, and the arrays are connected to a charge controller, so we can know how much is battery charging. I mean, the charge controller is then connected via switch to a battery, so we can know how much is charging. And from the battery, we have two outputs, one for DC loads and one for AC loads. And for the AC loads, it goes through an inverter. And currently, for a project that's happening right outside, we have DC lights and a fan working along with it.
Okay.
This is just our solar module. It has a maximum power output of 305 watts. So we have two of them connected in series. And there's a bit layout of Raspberry Pi. We are using a Raspberry Pi 3, and we are using an analog to digital converter to convert our signals from analog to a digital value, so we can monitor values using a computer. This is the diagram of the cost. So the total cost is around $1,300, but it's very important to remember that the 2 solar modules were provided to us by the mentors. So the cost can go up to like maybe $2,000 depending on it. Another important thing, so the blue part of the pie chart represents the PV arrays, how much the PV arrays cost. And that's why if you're using 2 PV arrays, it might cost up like $800. And our lithium iron phosphate battery, that's a 48 volt, 20 amp hour battery that costs around $650.
Okay.
And this is just a part of the pie chart. It shows the rest of the amount, how much, like depending on $1,300, like that's a small section of it, but like it mainly depends on how much you spend on the battery and the solar modules. Oh, this is our work, what we're doing throughout the past year. So on the diagram on the bottom left is myself and Salar Chauhan working on soldering. And this is Daniel implementing a AC breaker, us talking with Stuart Bowden in the middle. And on top right, you will see Ahmed working on the Python for the Raspberry Pi. And so the bottom one in the middle, that's why we call it the power crate. So it's actually a crate. It's a big black box where the initial, all the equipment, including the battery, the charge controller, the inverter, everything is inside the battery. So idea is like, and we have provided a disconnect outside for the solar modules. So anyone can buy this crate from, like we're not actually selling it right now, but in the future, hopefully someone can come up with a business plan. And thing is that someone can buy this crate and like connect it to the modules, charge their battery, disconnect it, take it anywhere they want, and use it for whatever loads they have. And this is just what our suggestions are for the future. So we were limited by the amount of budget we had, so we couldn't implement a refrigerator or something like that because of the cost. So, but like, this is a very scalable system. You can go up to like 50 amp hour, maybe 10 amp hour battery, and like depending on the load requirements, you can scale the system. Like meaning the sense that the same box can be used for how much ever you want to scale the system to.
Awesome.
All right.
So, what was the hardest part of this project, do you think?
Hardest part of the project is would be, so we had a very limited amount of budget. So initially we were like, oh, let's implement the refrigerator. Why not let's implement the refrigerator? And like, because we want to make sure that, so our idea was come up with a design that people at Monument with Cali can use. Like refrigerator, we can't live without refrigerator. So we want to make sure. So we were so we had a few back and forth with our mentor, making sure that our design was we stuck to the budget. And second important part was that, so 2 of my friends, they were working on the monitoring system part of it. So they had to learn Python to do the program Raspberry Pi. Good for them that they took a course in Python, so they made it slightly easier for them. And I'm very glad that they were in my team, yes.
Okay, awesome. Well, thank you for coming in and sharing your project with us, and good luck to you out there for the presentation. All right. So can you tell us a little bit about what you've done this semester, and then introduce yourself, and yeah, pretty much.
Yep. So my name is Matthew Copeland, and I worked with Justin Givler, Elise Matherly, and Daniel Moreno. And we are Team 33. We designed a keyless entry door lock for your home. So we kind of took the idea from keyless entry in modern cars, when you walk up and you just can get in your car and leave without having to unlock it. And so it's the same concept for your house. We designed a little module that fits in your pocket that's Bluetooth, and when you walk up to your door, Bluetooth connects to a module on your door, and then it'll send a complex code that changes back and forth to each other, and then the door will unlock. There's also a tiny camera above the door lock, and it'll take about 10 pictures every time the door is unlocked, so that you can see who's been coming in and out of your house.
Oh, cool.
And then it also sends the status to our website, and so you can log in and see when your door was locked and unlocked with a timestamp.
And are the pictures also uploaded to the website, or?
That was our initial goal, but right now they're on an SD card on the back of your door. So in the future, that's one of the main things we'd like to change is have the pictures uploaded.
Okay. Do you have a little video here to show us?
Yeah. So this video on the left, I've got our website. We kind of did a facelift to make it more user, to make it easier to read. But so the website on the left and on the right is output from a hardwire connection to your door lock Arduino. So it's so it'll tell you the logic that's going on. So I'll go ahead and play it. In the middle here is that's a little door we built with the door lock on the back. So the door lock is a quick set door lock. We took the motor from that. Then we've got it plugged into an Arduino that takes pictures, an Arduino that does all the Wi-Fi stuff and communication with the fob. And then on the breadboard in the upper right, it's got the Bluetooth module. And so this isn't a demo. He just shut his door and it's unlocked. And so he's about to walk away right now. And you can see the camera and on the front there. And as soon as he walks away, the door will lock. So it's locked right there. You can see, I guess we missed the actual lock, but you can see the deadbolt. He's going to show you the side of the door in a minute. You can see the deadbolt. And then the same thing when he walks in, you just saw the motor flip, and so the door is now unlocked. And so that was updated to the website, and then on the right it shows our rolling codes and like the lock and unlock and whatnot.
All right, awesome.
So there's more to the video. I don't know how much time we have, but
yeah, you don't need to show the whole thing.
Okay.
Yeah, so after going through this whole process, what was the most difficult part of your project, do you think?
Let's see. I think system integration. So we could do a lot of the pieces of our project easily enough by ourselves. So like we could get the camera working fine, but then getting it implemented with the Bluetooth so that it took pictures when it unlocked or that it uploaded to the website. So we could do a lot of the pieces, but then putting them all together and having them automated was kind of a big thing at the end.
Yeah, getting all the parts integrated and working together. Yeah, it's always hard. What do you think you've learned the most from this project? Was it just a lot of the coding? Was it actually getting everything to work together? What do you or maybe it was something like time management or something like that? What do you think you got the most out of this project?
I guess I definitely learned maybe a little bit about being in a group. But I have had a lot of projects at ASU in groups, so I don't know. I did a lot with the web development, and I've never worked on a website before, so I've got a lot better understanding of how websites work, and they're actually a lot easier to get going than you'd think. So I feel pretty confident in that area now, which is cool.
So now that you've gone through this whole process and kind of how stuff works, if you could start another project or start over, what are some things that you would change now that you've learned all this stuff from this experience?
Let's see. I think I would make sure that we did more in the beginning of the semester to make I think we underestimated how much time it took to put things together, like I said. So we were thinking we were good because we had each of the individual parts mastered, but then putting them together it was so I think starting earlier on with and keeping on making sure that we think through everything about how the system's going to go together would probably be the biggest thing I would change.
So are there any products like this currently on the market, and then if there are, what makes your guys' product kind of stand out in terms of being compared to the other ones?
So I know there are some products that are similar, like the Ring doorbell. It's got a camera and it'll live stream your front door. And there's a lot of keyless entry systems. But I think one thing that makes ours good is it's all-in-one and kind of compact. And so it takes the pictures, it unlocks automatically when you walk up, and it does the website so that you can get a log. Yeah. So I think there's systems out there that you could put together to do what ours does, but ours might be one of the ones that does everything by itself.
Awesome. Well, thanks for coming in and sharing your project with us, and then good luck to you out there for the rest of demo day.
Cool, thanks guys.
All right, so could you introduce yourself and then go into talking about the project that you guys have been working on for the past year?
Yeah. My name is Eddie Lemus Roldan. I'm part of the EcoCar 3 project, part of Team 35. And our project is basically the ADAS, which stands for Advanced Driver Assist Systems for Object Tracking and Lane Detection. So the essential background for the project and the motivation was to have an efficient lane detector and object tracking using a simple camera input feed. A lot of the cars that you see nowadays that are driving like are Ubers for like autonomous vehicles. Right. They use expensive LiDAR cameras and other sensors which aren't really feasible for the scope of this project and for domestic use. So the idea was, again, with the input video feed, it applies a variety of filters such as grayscale, the Canny filter, and then it uses algorithms such as the Huff transform and the Viola-Jones algorithm to detect lanes and objects on the road.
Okay. And so what do you guys have today as an end product that you guys are showing to everyone?
So the end product is basically the software and the implementation of itself. It is able to take a video input, both pre-recorded and in real time, and then output the videos of the objects being tracked and the lanes that are being detected.
Awesome. So what do you think was the most difficult part of this project now that you've been through it all and looking back on the past year?
I would say for our team would be learning the different algorithms and the filters and exactly how they work. I guess between all of them, there's this idea of probability. So you assign different thresholds to basically indicate what is detected as an edge or what may be detected as an object, and basically finding a balance that is not too broad, but at the same time not too constrained, that it might miss a vehicle or it might miss an object or a lane.
Okay. And you said as a team that was the most difficult. Was there something else that was more difficult for you individually, or was it the same thing?
I would say the same thing. I just said as a team just because I feel like that's what the majority of our focus was on. But yeah, that would essentially be the main component of the process, the whole device and the software itself.
Okay. What did you think you learned the most out of this? Because a lot of people today have said that, as electrical engineers, we don't really have as much experience with, programming, and this seems very programming intensive. So is that something that you feel like you learned a lot about during this process?
Yeah, so I would definitely agree with that, just because that's the majority of what the project was, is basically going through different coding languages. We use Python and C++. This one is actually running in C++, and we basically had to learn from the ground up coding languages that we weren't familiar with, and on top of that apply OpenCV as a library that's open source that we also implemented into it, and learn how to apply those functions in code with no prior experience.
So you guys have a fully functional end product, but say if you had like an extra semester or extra time or even more money, like say you didn't have like a limited budget or something, what do you think is something that you would add to this that you think that could make it better?
Well, for the beginning of the project, the original idea was to actually have a development board that we can embed and put inside of a car, no matter what car, and take real-time input. But unfortunately, those are costly, and we contacted manufacturers, but none of those actually fell through. So then the end result was just focusing on the software, but that would be the main change I would have, is to have a physical product that you can put inside a car and actually demonstrate. And on top of that, if we had more money, if we had like X amount or unlimited amount, it would be to apply more sensors to have more accurate results.
Okay. And so now that you've gone through this for the past year, if you could go back to the past like a year ago and tell yourself like something that right when you started the project, like something you would do different throughout this process, what would it be? Like time management or something like that? Is that do you have any idea what that would be?
I would say time management, I guess, would be a big one, just because we did focus a lot of our time in trying to get that development board, which never fell through. So that could have been used possibly into maybe adding more functionality to the code so it can do other processes instead of just the simple two but essential ones that it runs right now.
Okay. And then, so let me think. What? I'm blanking out right now. I think I've gone through all my questions actually. So thanks for your time, and
okay. Thank you.
Good luck out there for your presentation.
Thank you.
All right, could you introduce yourself and then tell us a little bit about your project?
Hi, I'm Trent McDougall, and I worked on the team for procedurally generating digital integer adders. So what we did was we took a lot of like fundamental topologies for adders, and we applied them to the next technology node, which is ASU's. ASU helped develop it, called ASAP 7, and we learned a lot of interesting things about how there's these new constraints in the upcoming technology node that haven't really previously been an issue when designing these adders, and it's really limited our ability to make certain topologies. So with that information, we've made a lot more interesting decisions on what type of adders are good. So we really discovered these by procedurally generating them, so we didn't have to rebuild all these adders at different bit widths. So we essentially generated 3 types of files. We generated like a digital simulation to make sure we were actually building them correctly, an analog simulation to collect data on the ideal netlist to get like an idea of what we were building, and then we finally generated like a layout dictionary, and we used this layout dictionary to then place all the cells in a big layout.
So what is the application of this project?
So essentially, as technology progresses and we get to this ASAP 7 technology actually being used in like our mobile devices, our computers, we need to make these decisions that when we need to like do addition in a computer, which pretty much is the fundamental root of all processes, we need to use the best designs possible. So we need to know the energy, like the power versus speed delay trade-offs. So we need to decide on these new topologies. And if we know, hey, in this next technology node, this is the new topology that's going to dominate in speed and power, which we actually have decided on, which is a Capstone with some level of sparse, depending on what bit width you're applying it to. So with this information, we know that like previously we had a Skolansky topology, which was previously like kind of consensus. The consensus was this was pretty much the best on the 30 nanometer technology node. But now that we have all these new constraints, we're saying Han-Carlson is pretty much the way to go now, and we expect to see it in like new like processors.
Okay, so is what you guys were working on software based, like running simulations of like building these schematics of the adders, or was it a combination of software and hardware?
So it was all simulated hardware. So we were building hardware and then pretty much simulating it. We weren't taking anything to like dies or anything or silicon dies. We were pretty much building it all in software.
Okay.
With
kind of like Spice. Or something.
Yeah, and so like the 4 tools we used pretty much were Verilog to verify all our stuff, and it was also used in generating like our simulation narratives. And we use HSpice to test everything analog wise, and we used Python to create all these files, and then we use GDSPy, which is like a subset of Python that's used in making layouts.
Okay. So what do you think was the most difficult part of your project?
I think it was just kind of approaching it, honestly, because it was like, it kind of felt like there was really no way to start it, because we were essentially building a tool that is like that big, like there's like Synopsys would build. So it was very like daunting to start. And what we ended up doing was we just kept approaching it from like really narrow perspectives over and over again until we kind of like kept reapproaching it. So we started like in Verilog, and we built it entirely in Verilog, and we're like, wow, this is really difficult. Verilog is not fun to build entire new generations. And so we're like, why don't we do it in Python? We'll just print Verilog based on parameters. And then once we got to that point, we were like, well, why would we write like 2 files to print Verilog and Spice? Why don't we just print them in the same file and use it all in the same instances? That way we know that if the Verilog is printing an and the Spice is printing our known tested AND gate, we know that it's logically going to be valid if it passes the Verilog simulation. So that's what we how we didn't have to manually verify all our Spice tools.
Okay. And what do you think you learned the most from this experience? And it doesn't have to be something like, technical. It could be, soft skills and stuff like that.
Okay. I think a lot of it was none of us really had known or learned scripting at that point. So for me, it was a technical skill, because the only language that I really knew was like Verilog and C. So learning like Python was and a little Perl was extremely helpful just for any application in any field, pretty much.
All right. Awesome. Well, thank you for your time and coming to share about your project, and good luck to you guys out there during the demo day.
Thank you.
Us a little bit about your project and introduce yourself, and just tell about what you've been doing for the past year.
Yeah. So my name's Nick. Am I looking at? All right. My name's Nick. I'm with Team 46. We worked on the ADSB transponder. ADSB more or less stands for Automatic Dependent Surveillance Broadcasts. Just kind of run through the slides a little bit. Basically, why it's needed is the older system's radar required planes to communicate with the ground, and the ground to communicate back with planes. It took a long time of delay, had issues in areas that had a lot of planes, a lot of weather, particularly Alaska. So the FAA commissioned this project they called Capstone, which essentially took all the products that they could have done and integrated in one with GPS, barometric sensors, planes broadcasting their own position, and they ended up mandating that all planes need to have this by 2020 because it was so successful they dropped accident rates in half. So our group wanted to do this mainly because one of our team members has a plane, and if you don't have it in there, it's going to be grounded by 2020. So now there's a lot of solutions out there. There's in and out. We wanted to do both, so you could both send your position and receive it. And the problem is cost is very high. So it's $5,500 for a system that's going to do what we wanted to do. So even for the cheapest one out there that basically just meets the requirement, it was about $1,000. So our group wanted to create this complete model and also keep it at a cost about half of what the cheap it is, a tenth of a comparable model, while still meeting all the FAA standards. So our group split it up into sections. So there's the pilot interface and the transponder. The transponder itself has three subcomponents: the radio, the avionics interface, which is what talks to the rest of the plane, and then the power supply is to give it all its power and be able to boost the signal. So our team members are Alex, who's out in North Carolina. He's got the plane. He was going to do mainly most of the testing, and he's the one who wants it for his own plane. There's Abdullah, who's handling all of our power supplies, and myself, who's handling the avionics interface. What we were able to complete was the pilot interface, which allows the pilot to talk with the transponder. We were able to work on majority of the transponder, including the avionics interface, which you can see the circuit board. Power supply is still in development because it requires 250 watts of power, which was creating a lot of heat issues and just trying to figure that all out. We do have some models that we're working off of, like the one shown here. The radios are completed. You can see a couple of the handmade circuit boards we made for that. They are fully functional and able to send and receive the frequency bands. And you can see kind of how it would work if we were building into a case and connecting it to the antenna. It would receive these signals into the avionics interface, decode it through a couple different microchips. And we, fortunately, due to a lot of technical research, we did start on a project called the Autonomous Lawnmower, but just trying to work between North Carolina, myself out in the Far East Valley, and then our student who's on campus, there's a lot of logistics issues. So we ended up switching to this in November, working with our professor to figure it out. So as far as our requirements, we did not completely finish it, but with a little more work, we'd have a completed product that would meet all our specifications. We came in at a cost of about $549, including the projected sheet metal and 3D printing cases to attach to a plane, and it meets all the FAA standards. So that's what we've been working on. Do you have any questions?
Yeah. So you said that one of your team members is in North Carolina, and then not everyone's physically on campus. So can you talk about that kind of experience, working with someone that you can't always physically see and talk to?
It was a little bit difficult for that kind of communication. We had about 3 different ways of communicating: Google Hangouts, Slack, Google Drive, where we exchange documents and schematics and stuff like that. But overall, working through those kind of issues, we were able to do quite a bit with it. And so I don't see it as being much of a hindrance. It's just sometimes that time barrier, that physical barrier. I mean, even if we're local, we still have to arrange to meet times and still communicate. So.
So what do you think was the most difficult part of your project?
Definitely trying to put it all together, honestly. There was so many moving parts to this. There's a lot of requirements as far as it meeting the FAA regulations. There's a standard we worked off of called DO 260B, and it required a certain type of GPS standard, a certain type of barometric standard. We had to factor in the fact it's going to be up in a plane or down on the ground, so there's a lot of issues of how to, manage the heat dissipation. As far as how to communicate, because it has to be able to talk to the plane as well as the other components. So we were integrating CAN bus, we're working on RS422 transceivers, then be able to talk to the rest of the plane. It had to decode signals from the radios, so there's a lot of moving parts to be able to bring it all together, and it ended up being split across 4 different circuit boards, so all the different connections involved with that.
All right, cool. Well, thank you for coming in and sharing your project with us, and good luck to you out there at Demo Day.
Definitely. Thank you. Oh, sorry. Didn't mean to throw it on the floor. Thank you.
Only? I'm not showing you. Oh, yeah, well, yeah, show him first, okay. And then once Malcolm starts talking, then just cut to the computer.
So could you tell us who you are and then go into detail about what your project was?
My name is Malcolm Regan. Team 30A, our project was to design a silver nanoparticle coating to improve the long wavelength response of thin silicon solar cells. Thin silicon solar cells are of interest because they require significantly less material to make, and so are significantly cheaper, and also they're flexible and so can be installed in places that other power sources cannot be. And but as cells get thinner, they suffer from low efficiencies at longer wavelengths. Like you can see in this graph here, as the thickness decreases, so does the efficiency at low frequencies. And a solution to this is a plasmonic particle coating. Plasmonic particles are small particles that, when smaller than the wavelength of incident light, the electrons within them oscillate, and so we use this to scatter the light. So these particles in a certain configuration or in a certain periodic array can be used to trap light within solar cells. So we designed the coating using MIT electromagnetic equation propagation software, MEEP, and we simulated this structure for varying particle radii and varying coverages, which was controlled by the width of the cell being simulated. And we got this to report the energy enclosed in the silicon. And this is an example of the result. This blue line shows what was the simulated enclosed energy in the bare silicon, and the red line shows the enclosed energy in the coated silicon. And from left to right is increasing radius, and from top to bottom is increasing coverage. You can see for low coverages and large radiuses, the light trapping effect improves in the coating. And so we chose to implement a coating of 100 nanometer radius particles at 10% coverages, just due to availability and stuff like that. And so to deposit the coating, we intended to use a tool developed in Dr. Holman's research lab, but the solution for 100 nanometer particles was only available in extremely dilute concentrations, which were not compatible with the deposition method. So instead we used forward displacement atomization followed by hot plate evaporation, which is essentially just using a spray bottle to spray it on the cell and evaporating the excess liquid. And here's some STM pictures of the cell after deposition, and it left behind a slight residue. So then we tested the coated cells, and it turns out that the cells across the board slightly degraded after in terms of IV characteristics after deposition. And our main result was the external quantum efficiency. We were trying to get an improvement on this on the right end of the graph at 1100, but we saw no such improvement. And for some strange reason, we saw slight improvement at short wavelengths. But two things that we should have done was the model we used to simulate the structure was oversimplified. We just simulated bare silicon when in fact the actual cells have anti-reflection features. It has an indium tin oxide layer, and it's textured, and that affects how light interacts with the cell a great deal, and so is an important consideration for designing a coating to trap light. And the residue left behind after deposition accounted for much of the degradation of the cell, and this could be solved by using a less dilute solution. And a lot of people helped out with this on campus. Since we're online, I mean, since Byron and Mengele did go down to do some measurements and observe the deposition, but I mean, we had a lot of assistance with stuff on campus. And I hope that explains. Do you have any questions?
Yeah. So, what do you think was the most difficult part of your project? I guess you kind of touched on the not being able to be on campus, but technical wise, what do you think was the most difficult part of it?
Well, we all we divvied it up. I mean, it was all from the background research it's sort of not too well developed, so that was really difficult. Just getting a feel for how this stuff worked and how to best implement it. And then simulation was also another huge it was a big bottleneck, and it was a big hurdle. So that was also a challenge. We didn't know MEEP, we didn't know anything about that. And then experimentation was also, we had to do an impromptu deposition method when we found that it doesn't, so there was a challenge every point of the way, but so we learned a lot.
All right, cool. Well, thank you for coming to share your presentation with us, and
thank you.
Yeah, good luck to you for the rest of demo day.
project. It was called the Mix Fix. It's an automatic.
Hold on yet.
Yeah.
Richard here needs to introduce you first.
Oh.
Yeah.
Or at least get started.
Yeah, get
All right,
started.
hold on.
All right. So yeah, could you introduce yourself, and then we can go into talking about the project that you guys have been working on for the past year.
Absolutely. My name is Dale Moffitt, and we're Team 50, and we've been a team, like you said, for the whole last year. We started meeting each other last September. We're an all online, all remote team. I live in Oregon, up in the Willamette Valley, and the other three teammates, Eileen, Ryan, and Tope, all live in the Houston, Texas area. So Tope and Eileen were actually able to meet up and finish the last little bits of our demonstration, so that was really helpful. But I would say one of the biggest things that we all learned was how to work from long distances away. So let's see, I guess I'll just jump right in here to our presentation. Like I said before, this is an automatic drink mixing robot, and it was a sponsored project from Garrett Scott, who works for Microchip Technology. He sent us a lot of the components that we actually used, which that was also a very good skill that we got from this project. Was we were using a lot of just off-the-shelf industry type stuff, and not necessarily stuff that we've been learning in class. I mean, we knew how to solve problems and stuff from being in college, but no actual direct correlations between what we learned and how to, say, program and code things or working with wireless connectivity. None of that was actually learned in another class, so that we learned all that just on the fly as we were going through this project. So the basic gist of the thing is it's going to be small profile mounting ultimately underneath your countertop or underneath your cabinet right over your countertop. The drink bottles would be located kind of on the backsplash area, and it'll be a cell phone app is going to be the main user interface. And so after a couple clicks and entering in your IP address and connecting to your home Wi-Fi network, you'll be able to get things ready to go. So this is a picture of the AutoCAD dimensions and drawings of what the final, and also a view of the final assembly. A lot of this plastic stuff was actually 3D printed. So that was a pretty cool experience, learning what worked and what didn't work as far as 3D printing goes. And of course, inside here you can see all the components. All this stuff up here, this is the microcontroller board and the Wi-Fi chip provided by Microchip Technologies. All this other stuff was readily purchased off of Amazon. So going into the control aspects, this was actually my role in the project. We were able to leverage a lot of Microchip's integrated development environments that it made it really simple. They've kind of made a way so you can do a lot of coding without actually writing code. They have a graphical user interface where you just select things with a mouse click, and then it creates all the different files that you're going to need. So header files and basic functions for setting and getting values, for instance. So it saved a lot of time for us in there. Another thing I wanted to highlight is this device is extremely low in power consumption. This is important because if we wanted to use this in our careers, in our industry, the industry is moving towards wireless technology. This device uses very low amounts of power when it's on, and even less, hardly detectable actually, when it's in sleep mode, and it's able to wake itself whenever it receives a command. Moving on to the communication, this was Tope's role in the project. He was able to create an app for the iPhone, and you simply input your IP address for your home router system, and then password if you have one. And then you'll be able to have a list of drink recipes available. Now this is, I guess, almost infinitely expandable. We went with a few choice selections because we wanted to use vodka as our base for our alcohol, and then the different recipes are crafted off of that base drink. But like I said, it can be expandable in the future. Here's a quick look at some internal wiring components. The main power supply is a wall wart type 12-volt power supply. And we also have a buck converter here to just the control power for both the relay board here and the microcontroller uses 5 volts. So we got 12 volts coming in and 5 volts going out to there. And the motor, there's 6 pumps total, 5 for drinks and 1 for a water rinse. So that's a neat little feature that we put into our drink mixer. It will, and you can see that on the video, which I think I can bring up something for that here. Let me. Sorry, this thing keeps popping down in front of my tabs. So.
Yeah. Hey Dale, after the video, we're a little out of time. So after you show the video, then we'll have to kind of wrap it up a little bit.
Okay. Sorry.
No, you're completely fine.
So this is one of the videos showing, I think, the basin rinsing and draining, and then rotating. So, all right, yeah, I'll wrap it up and call it good.
All right. Well, thank you for sharing your presentation with us, and good luck for you for the rest of the presentation time at Demo Day.
All right, thank you.
All right. All right, so could you introduce yourself and then talk about the project that you guys have been working on for the past 2 semesters?
Okay, sounds good. My name is Matthew Ito, and I'm in Team 13, which is this digital pitch correction microphone preamplifier. Our project is a microphone preamplifier, you might have guessed, and the idea was to include a pitch correction algorithm that allowed vocals to be corrected in real time. So if you're unfamiliar with microphones or just digital signal processing like I was when this project started, the microphone, the transducer in the microphone produces a small electrical signal that corresponds to the voice input or sound input that's going into the microphone. However, that transducer itself doesn't make it a large enough electrical signal for the actual studio equipment to use. Oh, what is this? Cancel that. So what happens is there's usually a piece of equipment called a preamplifier in the circuit. They'll amplify that signal up so they can actually be used by the recording engineers, the studio engineers or whatnot. So those are pretty standard. That's a normal thing. What we were trying to do is include a digital pitch correcting element, algorithm in this recording chain to try to help smooth out some of the vocals as they go into the microphone or as they go into the system. So this is our prototype. This is the actual pitch correcting hardware. There's another portion of the project that's the actual preamplifier portion of the hardware, but this is what actually did the magic, that actually corrected the vocals or whatnot. Let me go over my team members real quick before I forget. So we had Skylar, Trevor, Christoph, and myself. Our mentor was Professor Spanias. Okay, so this, like I said, was the actual pitch correction hardware. We had several features on it. The big thing with our project was the actual pitch correction. The microphone preamplifier is an important part of the circuit and is what it was going to be obviously attached, but this is what took the most work, is getting this to work. So you can see the several parts on this. They had the single board computer, which is SPC. It's a Latte Panda. It's a Arduino device that our programmer Christoph actually used to do the digital pitch correction. Mic in, audio out. There's a small OLED screen, like a what is it? LED screen. I think it's 3. So you can see that down there. Control knob to actually manipulate what's on that screen. We have the power input, a USB serial adapter, and then we had a fan to control for overheating. So this is the overview of the system. The actual system you saw would be actually connected to a controller PC. There'd be a program running on that PC. But the signal chain, so you have the signal coming in, that would be the microphone transducer, the microphone signal. It go into the preamp part. So in this particular, this diagram was made by the guy who was working on the that physical digital processing circuit. So he didn't have the preamp itself, but the idea is it goes in here. It uses an algorithm called Pasola and an algorithm called Yin to detect frequency and to shift those frequencies to the desired ones. And then you can either, you can either record the signal after that to the signal out. You can record it. You can play it back to the person singing so they can kind of hear themselves. There's several different things you can do. So this is what I was saying before. You input the signal. It goes into an input buffer. The Yin algorithm is the frequency detection. It figured out what frequency that note that you're currently on is. It determines whether it's added tuning. I'll talk about that logic a little bit later. It calculates the correct pitch, shifts it with, that's a typo, but shifts it with Pasola, the Pasola algorithm, into the output buffer, and then output signal either goes to the headphone of the singer or into a studio equipment to record it or whatnot. So I do have a video. It's not actually embedded into the presentation. I'm not sure if you guys wanted to see that, but basically what this video shows is the actual pitch correction software working. This is on the controller computer I talked about.
Actually, we're running a little out of time.
Oh, okay, so yeah. I figured it wasn't gonna be a whole bunch of time for that kind of stuff. So, I can skip ahead to the just kind of how the logic works. Let's see. So this is kind of the meat and potatoes of the project. What it does. So if you're familiar with music, what it does is you can tell it what key you want it to be in. So we say the person's supposed to be singing in C major key. So first it picks an octave, then octave key, whatever, next by notes of that octave, and then in that key or octave or whatever, it's going to know, okay, everything that's in C major is going to be a C, a D, maybe an E. I don't remember the actual the actual C major chord or the C major key by heart, but it will know those notes, and then we'll try to correct to the closest note that's at. So we'll say the frequency is a 380, and that C itself is like 400. I don't know what it is actually off the top of my head, but it would try to correct up to that.
Okay. So yeah, I think that's about all the time we have. But
okay.
Thank you for explaining your project to us and showing us how it works. And good luck to you for the rest of demo day and your other presentation.
All right. Thank you. You have a good day.
Thank you.
My name is Dustin Ellen. I was on a team with Ashkin, Timothy, and Jasper, and we worked on a phase-changing project for SRP. I'm holding a piece of phase-change material right here. You could think of this as a thermal battery. One of the big problems with power today is power storage. So this is a little bit of a different approach to it. It's passive storage. So the theory is you use your air conditioning to charge this during the off-peak hours, and this will freeze between 67 and 76 degrees. This will freeze into a solid, and when it goes through its phase change, going from a solid to a liquid again, it absorbs quite a bit of energy from the environment. So it's currently used commercially. They'll place it like above grid and ceiling tile and stuff like that, but it's not really used residentially yet. And the problem statement we were given is to be able to install this in a non-invasive approach for all the existing customers out there on the grid. So we tried some different things like putting it in paintings, putting it in furniture and stuff like this. And as you can see somewhere back here on the model, there's a model home we did in 3D, but we actually did that real live version of that out at the Polytech campus. It was 180 square foot. And using 26 pounds of PCM, we are able to come up with a 10% reduction in power consumption. We actually shifted the load by 2 hours. And so this PCM costs currently $2.85 a pound, and you need about a pound per square foot for it to be effective. So the price isn't really quite there yet for the average consumer, but we're thinking in the future that as the price point comes down, this is something that consumers could really utilize to not only save energy, help be greener, because the whole thing is utility company builds their power plant for the very worst hour of the very worst day, which is sometime in the summer. So their utility plant has to be built really big for that very worst hour, and rest of the time they're not using all that, but they have to maintain it, which there's a high cost to that, which is translated to the consumer. So by shifting the load, if half the people on the grid were able to shift the load, it would reduce the size of the power plant dramatically, which in turns would be savings for everybody. That's kind of what our project was about.
All right, cool. So what is your final end product that you have that you're displaying out there for demo day right now?
So our actual model was we modeled an actual home. So what we have out there is a scaled down version of the home, and we displayed kind of some cutaways of how we utilize this stuff in the furnitures and some paintings and end table. And that's what we did in our real life model.
Okay, so you basically take this and you put it inside like a couch or something.
Yes. So
Okay.
you could line the whole back of this thing. So this is just one packet, and it comes in a big sheets with a whole bunch of these packets glued together. So you could, essentially line the back of this, and it wouldn't, you wouldn't be able to see it out here, but it would add that insulation and factor to your room.
Cool. So what do you think was the hardest part of your project?
By far, software called Energy Plus that the Department of Energy uses. So we used a mathematical model. Originally, the mathematical model was supposed to be there to give us an idea of where to go with the real world model, but the mathematical model, which was Energy Plus, gave us a lot of problems. But at the end of the day, we got it working just in time to back up the data that we found in our real world model. Energy Plus is a program that's put out by the Department of Energy, and it's got just a lot of layers. You're basically building a building from scratch. You're saying this first layer is drywall, and this second layer is R11 insulation, and we got some PCM, we got wood studs or this type of wood. So it's a very detailed program.
Yeah. So what do you think you learned the most from this project?
So going into this project, we actually did a lot of research after we were given the problem statement, and we didn't believe that we were going to be able to achieve the results we did. I think it was our approach, possibly, that from looking at other people's failed approaches, because this problem's been presented to a few different classes. A lot of that, I think, is where we place the PCM. We use thermal imaging to kind of find the hot spots of the room, and for this stuff to be most effective, it has to charge and discharge completely. Because if think of it as a battery, if you've stored all this energy in your battery, you're not getting the most out of that stored energy unless you use all of it. So if it stays partially frozen, it's not working up to its potential.
Okay. Awesome. Well, thank you for coming in and sharing your project, and good luck to you for the rest of the time out there.
Thank you.